Okay, so last day of this unit for lecture, we're going to be doing a lot of practice, is determining delta G and its relationship to the equilibrium constant K. Where this originally comes from is this equation right here. This is not the most popular equation. I heard someone singing Popular earlier. One of the best musicals ever. Oh my God. Goosebumps, Defying Gravity. Oh my God, it's the best thing ever. So anyway, what this equation is, it's finding the non-standard free energy by adding the standard free energy to RT ln of Q. Since it's Q and not K, what does that tell you? We're not at, very good, we're not at equilibrium. So if we're not at equilibrium, this is the equation we're going to use to find the delta G that's not standard, the non-standard delta G. But if we are at equilibrium, Q turns into K. And what else is true about equilibrium? What does delta G equal? 0. And the delta G we're talking about equaling to 0 is your non-standard delta G. Okay, when we used ghetto homies and we said it was a phase change, it was at equilibrium, that wasn't necessarily a standard condition G. So what ends up happening is the non-standard G is what is equal to 0 at equilibrium. And so what we do is rearrange this equation, and this is the one that you're going to be using most often. I threw in a couple homework problems using this one just because for those of you who go to college and decide that you need to take chemistry or you want to take the class again, you will see that in a lot of the university courses. It's not heavily tested on the AP. This is the one you want to know, and I call this the negative rat link equation. Rat link, see how that kind of spells? Right? It's also up there. See the two rats? Their tails are linked. Our little characters, right up there. Okay, so that's delta G is negative rat link. One year someone came up with this. There's apparently a band called Ritalin Kids. So negative Ritalin Kids. And those are the kids on Ritalin. Yeah, they're jumping all over the place. Next to old Greg. Do y'all know old Greg? Okay, it's probably better you don't. All right, so what we're going to do, we're going to eventually apply negative rat link, but the problems we're working are just a smorgasbord of everything that we need to look at. So let's go to number 7. And it's going to take a lot of calculating, so we need to be on the ball here. Number 7 says the enthalpy of combustion of oxalic acid is 246.05 kilojoules per mole. So it's one of our few non-exothermic combustions. That is the enthalpy of combustion's delta H, or the combustion's delta H, its enthalpy. So they gave us a table here, and notice they gave us everything but the heat of formation of the oxalic acid. First part A and B are reviews, writing equations, writing formation and combustion equations. You guys did this in Unit 5. Write the balanced chemical equation describing the combustion of 1 mole of oxalic acid. So we're going to take oxalic acid and we're going to combust 1 mole of it. What's that equation? Plus what? Plus O2 gives us carbon dioxide and water. So I'm going to balance everything but my O's. So I need 2 C's and I've got 2 H's. At this point I have 5 O's on the right and 6 O's on the left. I got to get rid of 1 O. What do you think the best way to do that is? I can't change this. I'm only combusting 1 mole. How can I get rid of an O on the left? Put a half here, exactly. Jasmina got that. Good job. Green capacitor. All right, the next one. This is the one that made me flip my lid on 3rd period. Let's see if you guys can redeem my opinion currently of AP Chem students. Write the balanced chemical equation that describes the standard formation of oxalic acid. What's the formation equation? Creates what? Right. I need a definition. What? From what? Thank God! Yay! Give yourselves a round of applause because I pretty much wanted to quit teaching and go join like a colony of some sort and just drink Kool-Aid and squeeze grapes and drive away on my carbon wheels that I don't have, can go home. All right, so we're going to form 1 mole of oxalic acid from its elements. So when we're doing these formation equations, again, you have to have a 1 coefficient on that oxalic acid. And what elements make this up? 2 carbons plus no 1 H2 and 2 O2s. And that is a formation equation. All right. And I have absolutely no room underneath this to write the answer, but we'll figure out a way. Using the information given above in equations A and B, calculate the delta H of formation of oxalic acid. We don't necessarily need to use both equations, but do y'all have any ideas? Look what they gave us up here. That's going to be really helpful because we're looking for this. What is that 246.05? Where does that belong? It says heat of combustion. So which one does that go with? A. This is the delta H for A. If I know the delta H for A, and I know all the heats of equations except for that one, what can I do? Exactly. Make oxalic acid X and solve for it by plugging all the others in. So what I'm going to do, because the room on this page is not all that awesome, I'm going to write it in here. So my delta G is 246.05 kilojoules per mole. And I'm not going to write units with any of the others at this point because of the room. So I'm going to multiply 2 times CO2, products, sum of the products minus reactants. CO2's H is negative 393.5 plus 1 times water. Water is negative 285.8. Y'all see where I'm getting all these, correct? Products minus my reactants. I've only got 1 reactant, and that's what I'm looking for. That's my X. And then that oxygen's a free element, so that's going to have an enthalpy of 0. So the delta H of formation of oxalic acid is equal to, they got negative 1319 kilojoules per mole. I heard a yes. I heard 3 yeses. Good. Oh, one of them's twice. I guess it doesn't count but once. All right, got it? Questions? All right, I feel better than I did this morning. Thanks, guys. We're going to move on to part D of the same question. Calculate and this is kind of misleading. Turns out the delta S of formation is for oxalic acid is kind of already calculated. If you look back at this table, this is our delta S. And see, this is the delta S of formation of oxalic acid. So we already have that, and it's 120.1. So I don't know why the problem's asking for that. We already know it. It's 120.1. But I do want to calculate the delta S of reaction for the combustion of 1 mole of oxalic acid. So what do I do here? What? Big Mama. And I want the delta S for that combustion reaction. Which equation was that again? That was equation 1, wasn't it? Okay, so what was that combustion reaction? I'm just going to rewrite it here. Oh, there it goes again, being all weird. Oh, it's not at equilibrium. Okay, so what we need is to find the overall delta H of this whole reaction. And we're going to use everything from the table. So I've got all those numbers written down. Delta S of the reaction is equal to 2 times the CO2 is 213.6. I'm going to write the units once. It's joules per mole plus 1 times 69.96. Gosh, what is that coming from? Just ignore that. 69.96. I'm sure it's stressing Julian out right now. He's like, stop doing that, Demo. Don't mess up your hair, Julian. We were talking about your hair today. And that we can tell your level of stress by how high your hair is. Plus 1/2 of 205. Got it. And we are actually solving for delta S, not delta H. All right, so our delta S, when we do all the math, is equal to 275 joules per mole Kelvin. Okay, so we have the delta H for that combustion reaction, which was given to us. We have the delta S for the combustion reaction, which we just found. Now they want us to calculate the delta G for just the baby little oxalic acid all by itself, and then for the full reaction. So that's two separate problems. How am I going to find the delta G of formation of oxalic acid? What do I need to do? No, I don't know K. Ghetto homies, exactly, because do I not know the heat of formation of the G? Yeah, we figured that out in that one problem. Do I not know delta S? Yeah, it's in the table, so I can figure it out. So we're just looking right now of oxalic acid all by itself. So oxalic acid has a delta H. It was 1,319, but I want to get everything the same unit, and I'm just going to encourage you continuously to go to joules. That's always going to be your friend. 1,319,000 joules per mole Kelvin. Not per mole Kelvin, just per mole. Sorry, it's enthalpy. Minus, what are my temperatures of all this stuff? I've got little circles everywhere. 298. And then my delta S is in the table, and it was the 120. And that's in joules as well. So that's why I converted my enthalpy to joules. And so I end up getting a delta G of negative 1.35 times 10 to the 6th joules per mole. Someone check that? I heard a yep. Okay. So that's the first part. Now let's do the delta. What about the delta G for the overall reaction? What am I going to do? Big Mama. How do I do Big Mama for a whole reaction? What? I can only use the information in this problem. Okay, I can't go and grab tables. Yeah. We're going to do ghetto homies again, but now we're going to use the reaction values we have. This is the delta H for the overall reaction, right? Didn't we find the delta S of the overall reaction by doing Big Mama? So we have that value right here. So I'm going to use those values and redo ghetto homies again. All right, so my delta H was, I'm going to change that to joules as well, 246,050. And this is joules per mole. And then minus, we're still at 298. And the delta S of reaction that I just solved for was 275. And so I get 165,000 joules per mole. Is the formation of oxalic acid spontaneous? That's this one. This is spontaneous, yes. Why? Delta G is less than 0. Is the actual combustion of oxalic acid, the full-blown thing, spontaneous? No, because delta G is positive. You look perplexed, Hannah. Okay. But you understand conceptually. Okay. Number 11. All right. Delta G naught for the reaction was determined earlier. No, it wasn't, because we were lazy that day. So we need to find delta G naught. Since it's delta G naught, that's good news, because what does that mean we can do? It's at 298, so what does it mean we can do? No, we could do ghetto homies, but why would you want to, right? Because no, we don't use the word retarded. We can use Big Mama. If we were to use ghetto homies, we'd have to do Big Mama twice. Why? We can do Big Mama with just the delta G, since we're at 25 degrees Celsius. So go ahead and look at your tables and make sure I've got the right numbers here. Delta G, the last column, you've got coefficient of 2 times 51.31 kilojoules per mole is the NO2. Products minus the reactant of N2O4 was 97.89. And this is kilojoules per mole as well. So when they did the math, bless you, they got a delta G of reaction to be 4.73 kilojoules per mole. So just check the math. I think those numbers are right. Sound good? All right, now it says calculate the K. If we're looking for K, we're at equilibrium. What equation are we going to use? Ratlink. Don't always say negative Ratlink, though. I don't want you to forget that negative. Let's just talk about this equation for a second and why it makes sense. Do y'all know what the natural log of a number greater than 1 is? Positive or negative? Positive. Okay? Positive. So if I have a positive natural log of K, that's positive, with a negative in front of it, that gives me a negative delta G. What does it mean to have a number greater than 1? What's favored? Forward or reverse? I mean a K greater than 1. Forward's favored. So that would be spontaneous in the forward direction, right? So it makes sense that that would be a negative delta G. Okay? If I had a K less than 0, the reverse would be favored. So that would not be spontaneous in the forward direction. The natural log of anything less than 0 is a negative number. Not less than 0, excuse me, less than 1. Less than 1 is a negative number. Negative times a negative gives you a positive, which is non-spontaneous. Okay? So that's how that little equation works. So being that we are we spontaneous or not with this problem? Not spontaneous. What magnitude of K can we expect after plugging it into this? Less than 1, and we better get a number less than 1. But we got a problem. Can we plug that in as it is? Nope. We got to get it to joules because of the R. So I change it to 4,730 is equal to negative 8 point, it's the energy R, 8.31 joule per mole times the temperature. We are at standard conditions, so it's 298, and then natural log of K. So y'all know, hopefully know how to solve for inverse of K. And when they solved, we get a K of 0.148, which is definitely less than 1, non-spontaneous, in the forward direction. Okay, what about this next one? Calculate G. Is there a little knot up there? Nope. And they're saying, oh, we're messing with the pressures in the system, not necessarily concentrations, but pressures. So I got to find the G, not the G naught. So the fact that I mess with the pressures means I'm no longer at equilibrium. So what equation am I going to use? That non-standard one with Q in it. It's plus RTLN of Q, right? So what we're going to do now, do we have G naught for this? Yeah, it's right up there. But again, it needs to be 4,730 joules plus R. Let me erase that. That's a mess. R is 8.31 joules per mole Kelvin times temperature, 298. Now, Q, products over reactants raised to the coefficients in the balanced equation. What pressure do I put on top? I'll write out what we're going to do, the pressure of NO2 squared divided by the pressure of N2O4 to the first. So what do we square? 0.1 squared divided by 1, because those are the pressures they gave us in the problem. So when you solve all of that, this one I definitely want y'all to check. They got negative 6670 joules per mole. Hope it's right. Okay. All right. So it became more spontaneous, which makes sense because of the magnitude of the K originally. So, questions on this problem? No? All right. Moving on, 12. I feel like I've been talking forever. Kind of have been. All right, number 12. I like this problem a lot. It's kind of sexy. It tells us the concentration of the equilibrium constant for this reaction at 750 is 1.12 times 10 to the negative third. What would you expect this value, or would you expect this value to increase or decrease if we drop the temperature to 300? Explain using words only, and not words. I'll show diagrams. So we're not going to do math here. What I want to do is talk about when we drop the temperature, what would happen based on some energy things. You already know. You just might have forgotten about this. If my K at 750 is less than 1, do you remember the equilibrium relationship? How would the hump look with a K less than 1? What's favored, forward or reverse? Reverse is favored. So would the hump be shorter going forward or reverse? The hump on the energy diagram. Reverse. So my hump would be, this would be the easier route, right? Correct? So this is the K less than 1. Is that endo or exothermic? This is endothermic. So that means this reaction has to be endothermic. If this reaction is endothermic, where do I write the word heat? On the left. If I write the word heat on the left, the question says if we drop from 700 to 300, what happens to K? If we take away heat, because we're dropping it, it's going to shift to the left. And what does that do to K? K gets smaller. K should get smaller. One more time. Because the reaction has a K less than 1, the little humpy thing is going to be easier in the reverse because the reverse is favored. So this translates to an endothermic diagram. If it's endothermic, heat goes on this side. The question is saying when we drop temperature, so when we move temperature, what happens to K? Well, taking away heat forces a left shift. If it shifts left, what happens to K? K gets smaller. Now what we're going to do is through this series of calcs, we're going to prove it. And we're going to see if that's really true. So calculate delta H and delta S for the reaction from the table of thermodynamic values in your textbook. So I'm going to stop the video. This is where I'm kind of going to let y'all do your thing. First 3 rows, y'all do delta H. Last 2 rows, y'all do delta S. Delta H is you change to joules. I'm pausing the video, and when I put the video back on, I'll have the values. And you're doing this using Big Mama. I'm done teaching Big Mama. You guys need to know how to do Big Mama on your own. Pause. Okay, so after some calculation and number crunching, we got our delta H to be 114,000 joules per mole, and our delta S to be 129 joules per mole Kelvin. If those of you at home didn't get that, stop the video and work it till you get it. So now part C, I've taken out this. Ultimately, they're trying to find K. We already know K at 750. We don't need to find G at 750 because we don't need K at 750. I just want to deal with that 300, which is what we're looking for. So if I need to find G, delta G at 300, what do I need to do now? ghetto homies using my above information that I just solved for. And it's going to be nice and easy since I did convert everything to joules. So my delta G is equal to my delta H of 114,000 joules per mole minus my temperature of, we're doing it at 300, times the S of 129 joules per mole Kelvin, my little Kelvin cancel, leaving me with joules per mole as my answer. And they got a delta G at 300 of 75,300 joules per mole. Yes. All right, we're almost done. Now, the point was to see what happened to K at 300. So how do we find K? Negative rat length. So I'm going to go ahead and move that up here. Delta G equals negative RT ln of K. This is why we wanted to be in joules the whole time. So we get 75,300 joules per mole is equal to negative 8.31 times the temperature of 300 times the ln of K. We're solving for K. I sure hope it's smaller than 1.12 E negative 3, or all of my chemistry that I've known and loved would be wrong. Yep, 7.63 times 10 to the negative 14. Is that smaller? Yes, our prediction was correct. So that was pretty cool that we could do that and predict that. And our prediction is correct. All right, last problem of the unit. I know you're sad. All right. Consider the following. Got an equation and they give you K. Using only the above information, find delta G. What are we going to do? Do I have G naught? No, not ghetto. You can try to do ghetto homies. Go for it. What are we missing? We tried to do ghetto homies. We don't have anything about HOCl, do we? So I can't do that. What else can I do? I don't have a delta H equal to that to get the formation of HOCl. What else? Yes, negative rat length. Do you see why? They give us K right there. So we're going to use negative rat length. Do y'all feel cheated that you missed that? Do you feel stupid? No, I'm just kidding. I don't know. Maybe you need like medication at 1 o'clock, Jasmina. Maybe your brain just shuts off. What's our temperature? I see a temperature. 298. Math is hard. Maybe math ruins your brain for chemistry. So they got a delta G of 5,970 joules per mole. Okay, so there's our delta G. Done. So this is the delta G of the reaction, okay, of the whole stinking reaction above. Now it tells us to use bond energies to find our delta H of the whole reaction. Bond energies, and I don't necessarily need the table now, and you'll see why, but we did do delta H with bond energies. We had a table. Does anyone remember the formula? Delta H of bond energies equals to bonds what minus what? Right. Write that down. What I told third period, I'm going to tell you, you're pretty much going to need to review all of Unit 5 to be successful in Unit 13. okay, because I'm not going to be doing a lot of reteaching of stuff we've already had. And it was stuff we had this year. I'm going to assume you know how to do the flippy thing and all that kind of stuff that'll turn up in these AP problems we're doing in the next few days. So what I want to do to show you why I don't need to drag that table out is because you'll see really quick. If we have this equation, we're breaking bonds. So our equation is water, right, plus Cl2O. There's a ClO, Cl. I'm not doing correct Lewis structures. I'm not doing lone pairs or anything like that. But we end up making 2 HOCls. And I just want to show you this because this is kind of interesting. What bonds are we breaking? How many HOs are we breaking? 2 of those. So we're breaking 2 OHs and we're breaking 2 CLOs, right? Everyone see that? What are we forming? 2 HOs and 2 CLOs. So what would our delta H be? 0. That's why we don't have to pull the table out. Joules or kilojoules? Just kidding. It's kind of funny. I thought it was, but. All right, let's keep going on this problem. Find delta S of the reaction. How am I going to do that? I've got, what do I have for the reaction? Delta G. I just found delta H to be 0, so what do I use to find delta S? Ghetto homies. All right, so my delta G was 5970 joules per mole K is equal to 0. I'm going to make it joules. Minus 298 was my temperature, and I'm solving for my delta S. They got negative 20.0 joules per mole K. Oh, you are correct. Delta G is just joules per mole. Jasmina redeemed herself somewhat. She's like, she went back 20 steps and she went up like 0.5 steps just there. Math is hard. Just stop. That should have made up for all the mistakes? No. No. You got to crawl a little bit more up that slope. All right. Now, last thing is find the delta H of formation and the S for little bitty Hockle all by itself. What are we going to do? Big Mama twice. And I'm going to, again, split you up. We're going to do Big Mama twice. You have enough information now. Well, what you're going to do is you're going to set each of these equal to the delta H. We'll do the Big Mama delta H, and we'll do the delta S Big Mama. And we calculated those values. This one's 0. This one, I forget. And you're going to use the information given at the beginning of the problem and plug in everything. And for HOCl, you're going to put in an X, and you're going to solve for it. So I'm going to pause the video. People at home, pause the video as well, and I will set this up. So here are the answers to our delta H and to our delta S. Now the last thing, this takes 2 seconds. We need the K at 300, so we're going to use negative rat length. I'll use a different color. And with negative rat length, we have the delta G right here. So all we need to do is plug that in. So delta G is equal to negative RT ln of K. And because I'm the epitome of laziness today, when I plug in my, is that not delta G? No, that's delta S. Ignore, this is delta S. So my delta G is found on the previous slide, and that delta G came out to be 5,970 joules per mole. When you plug that in with R and the temperature and solve for K, you end up with 0.0912. And just to verify, delta G was right here. Plug that into RatLink, and you get 0.0912. That is all of the lecture. We're going to practice, 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 online lab, due in class on Wednesday.